Welcome to this last screencast of Module 6, which is on current distribution. Current distribution indicates how the current varies over the electrochemical cell. Sometimes it's the case that at one place in the electrochemical cell, the current density is significantly higher than in another place. This can, for example, be the case for the porous materials we just discussed, but it can also be a result of concentration gradients in the cell. And you see here a picture on the right, and we will discuss this much further in Module 8. Now, an unequal current distribution can be an issue in electrochemical cells because it can potentially lead to local overheating or electroaging, which are undesirable. Often it's also unavoidable. So with these 3D materials, it's you just have an equal current distribution. So you have to basically, as an electrochemical engineer, you have to assess whether it's a problem that this current density is unequal, and how strong is the inequality, because a bit of unequal current distribution might not be a problem, whereas a strong inequality can cause the problems I just mentioned. Describing a current distribution in an electrochemical cell is not straightforward. You need to take into account a lot of effects, such as the ohmic drop, the overpotential, the concentration gradient, and the other effects. Now, if you really want to take all these effects into account, this leads to, basically for any electrochemical cell, this leads to a very complex mathematical puzzle, which is basically unfeasible. So therefore, in current distributions, we typically simplify. And you can see that here. So in the primary current density current distribution, we only take the ohmic drop into account. In the secondary current distribution, we take the ohmic drop and the overpotential into account. And the tertiary current distribution, we take the ohmic drop, the overpotential, and the concentration gradient into account. None of these takes these other effects into account, so that would be an even more complex description. But as said, that's never feasible. So we will just now briefly discuss these three types of current distribution. Let's start with the most simple current distribution, namely the primary current distribution, in which we only take the ohmic drop over the electrolyte into account. Now, here you see an example of an endless parallel plate. So the anode is at +1 volt and the cathode is at -1 volt. Now, what you can see here are the current lines and the equipotential lines, because you can see, for example, the anode is at +1, cathode is -1, then, well, as you would expect, the middle should be at 0 volt. And since the whole parallel plate system is equal, there's no difference between the left side and the right side. What's interesting to note is that the current lines are always perpendicular to the potential lines. Now, the current distribution for such an endless parallel plate cell is easy, and also it's relatively easy to describe for disk electrode geometry. But it can quickly become more complex, and for that it's very good if you practice using quiz question 6.4. And that it can become much more complex, I would like to show with this example. Here you see an anode, the red part, and a cathode, the two blue parts. On the right you see the current distribution as calculated with the computer program COMSOL. Now what do you see here? You see the red parts where you have very high current densities, and you see blue parts where you have relatively low current densities. Now this actually makes sense, this result, because here the red parts correspond to this position, and you can see that at this position you have a relatively short pathway towards the electrode material, and towards a lot of the cathode electrode material. So you expect high current densities there. Whereas here in these middle places where you have a low current density, yeah, that's because it's kind of shielded away from the cathode material. So you expect a much lower current density there. Now this is something you can only do yourself qualitatively, and you need indeed a computer program such as COMSOL to make these calculations. In the secondary current distribution, we not only take into account the ohmic resistance, but also the overpotentials. This basically means that we include the Butler-Volmer equation into our mathematical description. As you can imagine, this adds further complexity to this mathematical description. And again, you need computer software such as COMSOL. Well, what I expect from you in this course is that you qualitatively understand the differences between the primary and the secondary current distribution, and that you can also recognize which one is which. And for this, I advise you to practice with quiz question 6.5. The last current distribution I will discuss is the tertiary current distribution, in which concentration gradients are also taken into account. Now, to show the effects of such a concentration gradient, let's look at this example of a parallel plate flow cell. Here you see both the primary, secondary, and tertiary current distribution. Now, what you can see is that the primary current distribution, the black line here, you see this high currents at the edges, so these points. And if you have looked at the quiz question, you will realize why that is. Then the secondary current distribution has a certain smoothing effect. But then for the tertiary current distribution, we really see this large difference. And that's related to the fact that the concentration of the reactant is decreasing over the reactor. So we can get very high current densities in the beginning, but then the current density will start dropping because of the depletion of the reactant. So it basically means that our limiting current density is going down. So this can, as you can see, this can have a quite profound influence on the current distribution profile. Now, as said in the beginning, this is still a simplification because we don't take into account effects such as bubbles. Now you might wonder, when should I use which current distribution? For that you could use this decision tree, or you could also just use your common sense. So you basically have to think, you want to keep it as simple as possible, but of course you want to take all the important factors into account. So you have to basically answer the question, what is important, what is not important. So the first question you ask yourself, is solution resistance important? If it's not important, if it doesn't play a role for your electrochemical cell, well, then you don't have to bother with all this current distribution rules. You can just forget about it. So that makes your life relatively easy. If it is important, and most of the times it is, then yeah, you have to see, do I have large concentration gradients? If I have large concentration gradients, yeah, then I probably will need to go for this very annoying tertiary current distribution. If I don't have them, then my life becomes simpler, and I basically have to ask myself, do I have are overpotentials important? Is this a very slow reaction, or are these actually very fast reactions for which overpotentials don't play a big role? In the latter case, you can go for the primary current distribution. Otherwise, you have to go for the secondary current distribution. But yeah, as said, it's quite complex. So you could also say, I just start with the primary current distribution. Let's see what it does. Then move towards the secondary current distribution, and also, yeah, spot if there are any significant differences. And then based on that, conclude whether it's really needed to calculate these more complex current distribution, or whether the primary current distribution already gives you enough information. Well, in this course, you're not expected to make all kinds of complex calculations with current distribution, but as said, you're expected to qualitatively understand current distribution, and you should also be able to draw some of these potential lines and current lines as shown for the primary current distribution that you should be able to do as part of this course. So that already brings us to the end of module 6. So here are the key takeaways. 3D electrodes are really crucial in many electrochemical applications. They can be mesh type of electrodes, they can be porous electrodes, they can be gas diffusion electrodes. Then the parameters that are important for these porous materials are tortuosity, porosity, and interfacial area, and expect you to be able to make calculations using these variables. Then we discussed current distribution. Well, it's not something we like to have, but often it's unavoidable, and then we need to have a good understanding of how the system behaves, if it can damage, for example, our electrodes. And therefore we can use the different types of current distribution, the primary current distribution, the secondary, the tertiary. And as said, this current distribution is a complex interplay of ohmic drop, overpotentials, and mass transfer. So this is where I would like to conclude this module. Thank you for your attention.